Hey, welcome to an important part of topic 3. This is solving triangles. Solving triangles, what could that mean? Well, that's finding all the angles and all the missing sides in a triangle. Hey, what about this set of triangles up here? You've done some of this before. They're all right angle triangles. And that's a basic beginning point of trigonometry. You know what trigonometry is? Trigon in Greek, metri, triangle measurement, and we had some ratios we were using in the previous work that we've seen on this, and you would have had that in your previous study in right angle triangles, all of those there. Can you see in this one, opposite over hypotenuse for 30 is a half, and we can do it for all combinations of sides and angles. And of course, do you remember here, it's still based on, or rather our circular function definitions are still based on the triangle, only we're going to put it over here in a unit circle. And the x value is going to be the cosine, the y value is going to be the sine. Hey, that's all building up nicely. Well, what we now want to do is to say, well, hey, if we don't have right angles in the triangles like these two here, is it possible to find missing sides and angles? Is there another way of doing it? Because let's face it, although there are a lot of right angles in our world, all the walls and stuff are built due to the effect of gravity, I guess, at 90 degrees to the ground, lots of them, there's also a lot of situations where there isn't a right angle in a triangle. So let's have a look at that. Over here I've got this little diagram which I think you might remember represents the enlargement of triangles, and going to look at that as a further way of comparing triangles and finding lengths and angles. So, let's go. Our first stop is at Sokotoa again, right angle triangle. So let's go back and do a little bit of a review of that now. Here it is here. Just go up a little bit. Right angle definition of the trig functions. Here we are. Sine theta is side opposite over hypotenuse. Cosine of theta, side adjacent over hypotenuse. Tangent of theta is side opposite over side adjacent. Nicely summarized by Sokotoa. How do we see that? The sine is the opposite over hypotenuse. The cosine is the adjacent over the hypotenuse. The tan is the opposite over the adjacent. So when you're working with a right angle triangle, you go to the angle, you look out from the angle. That will be the opposite side. Then you go to the 90 and look out. That will be the hypotenuse. And the other side, by default, is adjacent, because that's probably the hardest one to make sure of, because some students get confused with assigning the adjacent side. So go through those steps. Number 1, go to the angle that you're trying to find or that's been involved in the problem. Look out. That'll be the opposite. Number 2, go to the 90 degrees. Look out. And that will be the hypotenuse. All right. Do you remember some of that stuff? Let's go down and see what we can do with it. Well, the first thing, of course, in this course you already know from the previous presentations that you are expected to know the sine, cos, and therefore tan of 30, 45 and 60. Or now that we've done radians, pi on 6, pi on 4, and over here, pi on 3. Okay, so let's just check those out as to why they are the values they are. If you were to draw a triangle with sides, each side 1 there and a 90 degrees, so this is isosceles right angle triangle. These angles would both be 45, wouldn't they? Side angles opposite equal sides. And then if by Pythagoras we worked out this side here, it would be root 2. Let's say we didn't know it. That length squared is 1 squared plus 1 squared by Pythagoras. And so L squared is 2, or L equals root 2. L has to be a positive, so we won't worry about neg root 2 is also a solution to that. So can you see then the opposite? Let's do this angle here, the opposite over the hypotenuse, which is the sine of 45 or pi on 4 is 1 on root 2, and the cosine is the same, isn't it? Because the side next to the angle also is 1, that's an isosceles triangle, so they've got those two results, therefore the tan is 1. Tan of pi on 4 or 45 degrees is sine over cosine, they're the same, so it's 1. We usually do multiply top and bottom here by root 2 to get an integer in the bottom line. All right, root 2 on 2, the same thing here, because the simplest third form is deemed to be that one where the denominator is an integer. Let's have a look at constructing a equilateral triangle now, all with sides 2. All with sides 2, and all the angles would be 60. Okay, and if we did that and then dropped a perpendicular down, here it is here, it would bisect the base and it would bisect the vertical angle. We're treating that as an isosceles triangle that way, perhaps, if you like. And then working in this triangle here, let's have a look. The sine of 60. So by Pythagoras, what is that side? Well, 2 and 1, that length, L squared plus 1 squared equals 4 by Pythagoras, and therefore L squared equals 3. L must be a positive, so it's positive root 3. Okay, so we can establish, therefore, the sine of 60 is opposite over hypotenuse. There's a hypotenuse there, or in this one, and the cos of 60 is a half, the same as the sine of 30. Okay, so you could see that, you could do the 30 in here as well, and just come down just a little bit here. And the tan of 60 or pi on 3 is sine over cosine, which is root 3. You can work that out. Dividing by a fraction, remember, you invert and multiply, getting root 3. And of course, if you just plucked that triangle out, you could do 30 degrees as well. The sine of 30 is actually the cosine of 60, isn't it? Because the side opposite the 30 in a 90-degree triangle is the side adjacent to the 60. So the sine of 30 is the cos of 60. The cos of 30 is root 3 over 2. So the tan then of 30 is a half over root 3 over 2, invert and multiply, be 1 on root 3. Or we could multiply top and bottom by root 3 to get the simplest third form, root 3 over 3. Okay, so these you're supposed to remember. So let's come down and have a look at the summary we've got here, taking some screen clippings from Pearson's. So there's the list of all of them. So perhaps copy those down. I'd be suggesting that you memorise the sines and cosines and work the tangents out as sine over cosine. All right, come on down and let's use some of this in right-angled triangles. First of all, there's a couple of definitions particularly mentioned in the syllabus, and that's the angle of elevation and the angle of depression. The definition of the angle of elevation is the angle from the horizontal that you must raise your eyes to see the object, angle from the horizontal to view the object, let's say. So you're going up, raising your eyes, so here's a horizontal line here, looking straight ahead. The angle of elevation is how much you've got to look up there to see the top of the object. Over here, angle of depression is the angle again from the horizontal, this time downwards. down that you have to look. So looking straight ahead, how far down do you have to look to hit the object? To view the object, I better put down here upwards, over on this side here, upwards for angle of elevation and downwards for angle of depression, always from the horizontal. Okay, so one thing you might notice there with the angle of depression, if that's a horizontal and this is horizontal, this angle here will also equal this one here. So that could be helpful in working in a right-angled triangle. So let's look at some of those practical problems with right-angled triangles, because there's a bit of a focus in this course on that sort of thing. So here we have the first problem, again screen clippings from Pearson's here. From the top of a perpendicular cliff 93 metres high, better underline that, and it's perpendicular. Not a bad idea to underline key words in a problem. The angle of depression is 26.5 degrees. Let's draw a diagram. Here's the cliff, where here's the horizontal, and there's the angle of depression. Okay, we're looking down at that boat. So we've got all our given information on the diagram, so that's important. Now, what are we going to do? I've just mentioned that before. If that's horizontal, that'll be parallel to the seawater there, which is going to be considered to be horizontal. Therefore, this angle by alternate angles is going to be this one and this one are going to be equal, alternate angles, because looking horizontally and horizontally here, they would be parallel. Therefore, we can rewrite the triangle. Not a bad idea. Pluck the triangle out and have a look at it. So what have we got? What have we got here? Well, here's the angle. Look opposite. Yep, we've got the opposite side. Go to the 90, look out. No, we haven't got that, haven't got the hypotenuse. We have therefore got or want the adjacent. So let's write down SOHCAHTOA and work through it. SOHCAHTOA. We have opposite and adjacent involved. Opposite and adjacent. So it's the tan of that will be 93 over D, or D is 93 over tan, 26.5 or 160.53, or round it to the nearest metre or to three significant figures. It says up here three significant figures. I should have underlined that up the top there. Okay, do you get it? Some interesting problems you can do with the right-angled trigonometry. Solving right-angled triangles is what we're doing now. Okay, a man who's 183 centimetres tall, what's this one? Casts a 72 centimetres shadow on the horizontal ground. Horizontal. What is the angle of elevation of the sun? The nearest tenth of a degree. Oh, getting very accurate. So here we are, we'll draw the sun. We've got a shadow coming down here, and he's 183 centimetres tall, and the shadow is 72 centimetres. So let's have a look at redrawing it. Pearson's haven't done it this time. Let's redraw it. Angle of elevation is how much you have to look up from the horizontal, so that's the theta. This is 183 centimetres, 72 centimetres. Go to the angle, look out. What have you got? The opposite. There's it. Go to the 90, look out. Hypotenuse, haven't got that. The other one's the adjacent. So under SOHCAHTOA, we've got tangent again. Okay, because we're working with the opposite and the adjacent. So the tangent is 183 over 72. Inverse tan on your calculator, tan neg 1. So you go to the tan button, this is on the most calculators, and tan neg 1 is second function tan key, and you then get that to the nearest tenth of a degree. So they're interesting problems, aren't they? Exciting work in right-angled triangles there. Okay, so you want to do some. Let's come down to Pearson's 7.1. And I'll scroll through these slowly, and right at the end down the bottom are the work solutions as usual. Okay, so pause the presentation, have a go, and all different little variations here. Right, I'm going to give you the next lot, 20 onwards here. Okay, 20 onwards. We better just have a look back up here at questions 20 to 25. Find the exact value of theta in degrees without using a calculator. So these are going to be common angles. These are going to be common angles that you are supposed to know the sine and cosine and therefore the tangent of. So think about those. Okay, down to 37. You can pause it there. Let's go on now. In questions 38 and 39, solve for all of the unknown sides. So, quite often you'll use sum of angles of a triangle equals 180 to get the last missing angle. That's the quickest way of doing that. Okay, pause it, have a go. There are some interesting problems of a practical nature in here. Let's go down to the last couple then. 44 and 45, it skipped a bit there, we'll just bring back 43. The latter problem, quite a common type of problem. Okay, right, pause it, have a go. I'm going to go on to the solutions now. Let's go on. Okay, 7, there's 10 and 11 on the side there. Let's pause that. Go down a bit more now. 8 and 9, 12. (13, 14 and 18, 19 there. Go down. Let's go down a bit more, bring 15 up. Okay. 22, 26 there, all on the calculator. Okay, through to 28 there. Getting through them there now. Come up a bit. Alright, we'll go on. 39. Okay, and just the last little bit here now. (45), 42, 43 still coming up. Okay, 43. So they're fully worked solutions from Pearson's. How'd you go? Go back and check your work and make sure. And we can go on now. I've got an exciting question for you. It's coming up here. I'll just get it in the middle here a bit. Hey, what about working in non-right angle triangles? We haven't done that before, have we? So let's have a look now at what we can do in a non-right angle triangle. There's a few things. Let's first of all look at the areas. Okay. Now the areas of triangles. Well, you know what to do with a triangle. The areas are half base times height. Base times height. Okay, this is obvious here. In this one we have to construct the height in there, and in this one we have to construct the height. And I guess back in earlier maths you would have established no matter what the shape of these triangles, they can be considered to be half a rectangle of that base and height. And we can prove that. We won't do it here. But if you drew the rectangle through here of that equivalent base and height, that triangle in the middle is actually half of it. And we do it by looking at the congruence of those figures and the congruence of these two. Okay, so that all these triangles do follow the same pattern. The areas are half base times height. Hey, but what if you don't have this given like that? How would you find the area? Is there a way, without drawing that, height in there, of just using these sides or angles or something? Can you do it without constructing a perpendicular? Let's investigate that now. Okay, so coming down, here we have two situations. So I'm going to see if we can do it. We know that the area over here is a half B times H. Now B's all right, that's given. But can we work out an expression for the H so we don't have to draw it in? Oh, well, I think we can, can't we? We can say in that triangle standing up there, H is the side opposite angle C, and A is the hypotenuse, and here's the 90. So we can say that's opposite and hypotenuse, Sokotoa. Sine of angle C is H opposite over hypotenuse, H over A, or A sine angle C is H. Let's put that in place of H in here. What have we got? Got a half B times A sine angle C, or a half AB sine angle C. Hey, we've done it. If we didn't actually have H given to us, we don't need it. It's half the product of these two sides, sine of the included angle. And of course we could do it with another side over here. And we would come up with that result using that side, an angle A. Well, angle A would be useful then. Ah, that's interesting. Okay, what about over here where the height is external? Let's have a look at it. The area is a half base times height. We don't want to have to find that. Let's put the right angle triangle here that we have. Let's just get rid of this. So if we go down here, the right angle triangle that we've got, this time the angle is 180. Take the angle in here, which is C. Sum of angles on a straight line, sum of adjacent angles on a straight line, better said. So, what's H? Let's have a look. Here we can say H over A is the sine of 180 take C. So H equals A times the sine of 180 take C. But hang on, the sine of 180 taken angle is the same as the sine of the angle, same as sine angle C. Remember that from our unit circle work. If that was our angle theta and we put an angle theta there and made congruent triangles, the sine of that, they both have the same y's. They have the same sine. That would be 180 take theta. So we've got the same expression. It's a half B A sine angle C, or we usually write a half AB sine angle C. So it doesn't matter whether the height is actually external, that altitude is drawn externally. We can do without it. We don't need H directly. Let's come down and summarise it. Here's the area of a triangle now. If you've got triangle ABC, it's half the product of A and B sine angle C. But as with most formulae in maths, you should look at them generically. What's this really saying? We could draw the perpendicular from any of those sides. So really it's a half the product of two sides, okay, times the sine of the included angle. Okay, it doesn't have to be A and B. Okay, if we went differently, let's say A, B, so that's naming in triangles, of course, the side opposite the vertex big A is called little a, side opposite B is little b, side opposite C is little c. So it can be these two, sine of that one, or it could be BC sine angle A, or it could be CA sine angle B. Okay, any of those. Because we would just drop our perpendicular from a different vertex. Let's have a look at using it now. Find the area of each triangle, express the area exactly, or if not possible, to 3 significant figures. That's what the IB says at the beginning of their exams. So, what have we got? We've got 2 sides and this included angle, so it's half the product of 2 sides, sine of the included angle, and we can do it exactly. Let's go to this one. We've got 2 sides and the included angle, so it's half the product of 2 sides, sine of the included angle. That's a decimal here, so I round it off. So they've given us ones with all, which match up nicely. You must have the included angle from the derivation we just did. So it's half the product of 2 sides, sine of the included angle, and that again is not a terminated decimal, so we have to round it off and use the approximately signs there, those approximate signs. Okay, because we've terminated the decimal. Let's go down and have a look how we can use this, and this has been very popular in the IB examinations. Circle has a radius of 1 centimetre. Yep, I mark it indirectly. And this angle subtends an arc of 2 pi on 3. Find the area of the shaded region. This area of the shaded region, this is called the minor segment here. Minor segment, where a chord, a line joining 2 points on the circumference, cuts off a section. So this other part here would be the major segment. Okay. All right, so let's do it. How are we going to do it? We're going to do it by difference. We will get, here it is down here, we'll get the area of the sector there and take away the area of the triangle, and we'll get the shaded area. Let's have a look at it. Shaded area of the sector is half r squared theta. Or on the formula book it's of course half theta r squared, and theta is in radians. Okay, so let's do that first. Here they've done it, a half r squared theta, so that's pi on 3 centimetres squared. Now let's look at the area of this triangle. It's a half product of 2 sides, sine of the included angle. The 2 sides are both radii. So we've got root 3 on 4 square centimetres. And we are working out there the sine of 2 pi and 3, just think of what they've done here. We've done this in the unit circle work. Pi on 3 is there. If we go around 2 pi on 3, that angle there is pi on 3, the same as a working angle in equations. So the sine of 2 pi on 3 equals the sine of pi on 3, and the sine of pi on 3 is root 3 on 2. So that's where it came from. That's where this root 3 on 2 came from in here. So no need to use a calculator here. So the shaded area is pi on 3, the sector minus the triangle. Or you could go it over a 12, or you do it on the calculator as 3 significant figures. Right, just look at this. If it's in paper 1, getting over common denominator of 12, we have to multiply that by 4, therefore it's numerated by 4 to keep the balance in the fraction, multiply this one by 3 to get 12, and multiply its top line by 3. So do you get it? We have a powerful tool here in finding the areas of non-right angled triangles without drawing the altitude in. Okay. Here are some questions I've just taken from Pearson's, which come in at question 14. These are the interesting ones that you can now do that you couldn't do before, involving area. Okay, so pause the presentation, have a look, and I'll go on now. Okay, so we've got some solutions here. 14 and part of 15, just check them out. 15... 16, almost, we'll do the rest of that in a minute. B, and then going on to 17. Okay, so that's been good. We're working in non-right angled triangles now, no 90 degrees, so we find the area, that's handy. What else can we do though? Is there something else we can do? Oh well, we want to solve the whole triangle, don't we? Solving it means all the angles and all the sides in any triangle like this, no 90 degrees. Okay, so from Pearson's now. If the area of the triangle is half the product of two sides, sine of the included angle, there are three different pairs of sides and sines of included angles we can have. So if we divide all three of these by a half ABC, we get this expression here. And if we divide those, AB, look at what happens. That goes out and that goes out. BC goes out. So we get sine of angle C over the little side opposite equals sine of B over its little side opposite equals sine of A over little a. Oh, the ratio. This is called the sine rule. The sine rule. The ratio of the sine of the angle, of any angle in the triangle, to the side opposite is constant, and you can use it either way up. If you're trying to find an angle, you might use it sine of the angle on a side, or you could do it the other way up and put little c on sine C equals little b. If you were trying to find a side opposite an angle, it'd be more convenient to have that unknown in the numerator in normal equations, isn't it? Have it in the numerator. So here is the sine rule. The ratio of the sine of an angle to its side opposite is constant. That could be very useful. Let's have a look at it. Here it is here, law of sines or sine rule can be done either way. Later on we'll look at what the information booklet has for us and what they give us there, but you can think of it in either way. It's got to be a side compared to the sine of the angle opposite, or upside down. So that's the matching up there. Let's have a look now at doing something with it. So here we are. Find all the unknown angles and sides of triangle DEF here. We're given two angles, one side. All measurements to one decimal place. Okay, well first of all, by sum of angles of a triangle, 180, take the other two, gives us this one here, 54.3. The sine rule says the sine of this angle divided by its side opposite over here is the same as the sine of this angle divided by its side opposite. Okay, now I wouldn't have started that way. We see we need a side, so start off E over sine of 103.4 equals 11.9 over its ratios, 22.3, and then just multiply across by that, rather than having the unknown in the bottom line. Okay, so here's approximately this. Don't truncate it yet. If we need it later, we want more decimal places. Okay, so hold the decimal places. Let's look at this one. Write another proportion. What's this one? Well, D over the sine of 54.3. Again, I would, because I'm looking for a side, I'd use the ratio the other way up. Is 11.9 over the sine of 22.3. Multiply across, you get this one here, and there we are. So the other parts of the triangle, rounding them off finally, only in the last part, in case we wanted to use the previous value in a further calculation. Don't truncate it and then add to the errors there. So this is a powerful one, isn't it? Let's go on. Have a look at another example. So here we have a tree on a sloping hill casts a shadow of 45 metres long. It's on a sloping hill. So that's messed up our right angle triangle work. The gradient of the hill is 20%. Oh, 1 in 5. The angle of elevation of the sun is 35 degrees. How tall is the tree? The nearest tenth of a metre. Okay. All right, well, if the gradient of the hill is 20%. So that means 1/5. 20% is 1/5. So that's the slope of the hill. 1 is to 5. And so what is this angle in here? Alpha is, here we are, It's 1:5. This angle is 11.3099 degrees. Okay, so we're going to have to use that in a minute. So the height of the tree is h. The angle of elevation of the sun is this angle in here. This total angle in here. So therefore, beta is 35 minus 11.33. So we can do that, 11.3099. So the total angle of elevation, top of the tree there, is alpha plus beta. Now, this is a tricky little devil. So this angle in here is 23.6901 degrees. Using plenty of figures because we want to go on with it. Okay. All right, so what we've got there, then we can work in that triangle up here. Have we? Come on, let's undo it down here. Here it is here. We've got the h there, the 23.7. We knew the total of that was 35. This down here is a 90-degree triangle, so we know that this is 55, and they're describing out there some of the angles of the big right-angle triangle. So working in this triangle now, I'd encourage you to no, that's straight encourage you there to redraw the triangle with what we now have in it. We can say what? The sine of 23.7 over h is the sine of 55. Oh, sorry, that was 45 over 45. Again, I think because we want h, we'd use the ratio the other way up. Okay, with the sides on top. So we've gotten into a triangle that still doesn't have 90 degrees in it, but we are able to multiply across there and get this answer to 1 decimal place n, or 3 significant figures, be 22.1. That's a bit of a tricky one there, working between a right angle triangle and a non-right angle triangle with our sine rule. Let's look at another one. This gets interesting. So we've got two triangles here where HK is 18 and JK is 15, JK is 15 and JHK is 53. So don't know whether you realise that you can draw two triangles with that, because you can have a different length of side down the bottom. Okay, let's say we want to calculate the side of this size of JK in this triangle, and then calculate the area of the first one by the sine rule now, and we'll use it that way up. The sine of the angle over the side opposite is the same for all angles and sides. So therefore, multiplying across by 18, we get this one. And therefore, we can use the inverse sine on the calculator and find that angle. But hang on, that doesn't look right. That looks greater than 90 degrees. How can that happen? Uh-oh, we know, don't we? If you had 73.48 in here, 73.4 whatever, and we made a congruent triangle here with 73.4 there, the heights here, the y values will be the same, but the angle is actually that angle there, 180, or pi minus 73.4. So there are actually two angles whose sine is this thing here, because the sine of the angle in the second quadrant, 180 minus that working angle, is the same. So now we have a dilemma. It could have been 73.4 or 106.592, and that's what this was. This is the one with 73.4. That's one possible triangle, and then there's another one here where this is 106.6 or whatever. They add up to 180. Because of this business in the unit circle, it is possible to have the sine of an angle bigger than 90 and its sine is going to be the same as 180 minus 73.4, or its working angle. All right, so this is ambiguous. It's called the ambiguous case. In this problem, we are guessing that this is bigger than 90 because it looks that way. In a problem when it's not obvious and it's not stated, you've got to be careful with finding the angle opposite the biggest side, because it could be acute or obtuse, and the sine value won't tell you that. We're going to have a look at that in a minute. Let's have a look in triangle HJK. Well, we know that because the sides are the same here, let's just go back up a little bit. The sides were the same in these two triangles. All right, so this must be the 73.41, and so its areas are half the product of two sides, 18 by 15 by sine of the included angle, which is going to be 18, 15, sorry, this one up here, and we will use 73.4 there to find that other angle, 180 minus those two, 53.592. Then we can find that. So what they're trying to say here in Pearson's is that you can use this triangle and find that angle, it's bigger than 90, but just remember there's this triangle over here it's going to give you the same size sine, but it's for the acute angle. Okay, let's have a look at that in a bit more detail. Here's the ambiguous case. I'm going to say to you, I'm going to give you an angle here. Let's call it 43 degrees. Okay, and I'm going to say I'm going to try and find theta, this angle here. And this angle is going to be obviously the biggest angle. So this is where it's dangerous, because the biggest angle opposite the biggest side, see that biggest side there, could be bigger than 90, and I won't know. Let's work it out. So the sine of theta over 10 equals the sine of 43 over 7. So the sine of theta equals sine 43. It's been divided by 10. So I'm going to multiply by 10. And then theta is going to be the inverse sine of this thing. Okay, the inverse sine, and that's approximately 103 degrees. I'll round it off. Approximately, I've just messed the problem up. It's approximately 73 degrees. Okay, but it could be, or it could be 180. Take that. Hang on, 77 degrees. I just looked up on the calculator again. Could be 77 degrees or 103 degrees. Okay. Now, it looks bigger than 90, but we shouldn't be guessing. So this is called the ambiguous case. We shouldn't use the sine value to work out the largest angle. This is the largest angle because it's opposite the largest side. Okay, so when we do the sine rule on it, we get the calculator will always give us 77, the acute angle in the first quadrant. But of course, going back to our circular function work, if that's 77, there's another one over here, congruent triangles, that's 77 in there. What is it? 103. That would have the same size sine, and we don't know. Ambiguous. We don't know which one it is. Which one is it? Okay, let's just check that out now. This is why it happens, of course. Sine, cos and tan are all positive there. If you go into the second quadrant, sine stays positive. And if the triangles match up, there's one and there's one, this big angle theta will have the same sine as these two in here. You won't know whether it's the acute one in this quadrant or the obtuse one which is around there, which is in or produces a congruent triangle. So sine can't help you there. Notice if we use the cosine somehow, and it went into a bigger angle, the cosine goes negative. That could be worth thinking about later on. Let's have a look now at this ambiguous case and how it happens. We'll just go back up a bit here. Okay, so here we are. Let's start off with a, what did we have in here? 43 degrees. So let's draw a baseline of 10, and on the end of it, so we're starting here, that's fixed, and we'll go down here, so that's going to be fixed, and then we're going to draw this down here, 43 degrees, and this could keep going down here. Now, if we want 7 to be the length of this side here, there are 2 7s. You watch this now. I'm going to swing an arc from the fixed point of radius 7. Okay, so it's coming through here, coming through here, and there's my arc representing all points which are 7 units from this fixed point up here. It's going to swing through, so this would be 7 as well. Can you see that when we say we have 10 and we have 43 and we have 7, there are 2 triangles we can draw with 43 degrees, 10 units, 10 centimetres, let's say, and 7 centimetres. Because of these 2 positions on this 43 degree line, which are both 7 centimetres from the fixed point. And we don't know whether it's 103 or 77. So this is the ambiguous case. So we want to try and avoid finding the largest angle using sines, using the sine rule, because we don't know whether it's really 77 or 103. They have the same size sine. Okay, so there's a little rule. Avoid that ambiguity. If you can't, you really have to quote 2 possible answers, 103 and 77. You really shouldn't have a look at the diagram and guess that it's less than 90 or bigger than 90. And of course you only have to do it for the largest angle opposite the longest side, because there's only one angle going to be bigger than 90 in a right angle triangle, because the sum of all the angles is 180. So you only can have one bigger than 90. All right, think about those things. Let's go down and see if there's some other things that we can do now. And the law of cosines, was commonly called the cosine rule. Sine rule and the cosine rule. Okay, well let's have a look. Why do we need another rule? Well, we just mentioned sine doesn't tell us if the angle goes bigger than 90, that's in the second quadrant. But also, there are no angles here, so you can't use the sine rule. No angles. And here there's only one angle. There's only one angle. Can you find this side without another angle? Is it possible to have another rule to accommodate situations like these? Can we solve these triangles? Find all the angles and all the sides. Okay, well let's have a look and come down here. I've taken this derivation from Pearson's. Let's take a triangle with 3 sides like this. And we could draw it with a obtuse angle there as well. There are 2 situations. And can you see that point A up here in both cases, point A has an x-coordinate, so here that's the x-coordinate, and the x-coordinate here, if you take angle C, the x-coordinate is the adjacent over the hypotenuse. So that is, therefore, the x-coordinate is b cos c. Okay, let's just put over here, x-coordinate over b is the adjacent over the hypotenuse, which is cos of angle c. So x is b cos angle c. And what about the y value? The y value of this point is, let's do it over here, y over b is the sine of angle C. So y equals b sine angle C. And we can do the same thing over here if it's in that region there. That would be the x-coordinate of this point, that would be the y. So you come up with the same pair of coordinates. Okay, that's going to be important, because watch what we're going to do now. If we're trying to find, let's say we're trying to find the length C from this point to this point. Using the distance formula, the x-coordinate of the first one minus x-coordinate of the second, there it is. That x2 take x1 squared, plus y2 take y1 squared, which is only naught there. Okay. So we put our triangles, for a start, I should have said, we've located both triangles so that one of the sides is on the x-axis. There's no loss of generality there. We can just bring that down and put on the x-axis for simplicity. Okay, now let's square both sides. Let's go remove that root sign. Then if we expand both of the squares now, okay, first term squared, second term squared, and so twice the product, second term squared, and then this one is just b squared sine squared c. We're using the idea there of a perfect square. A take b all squared is a squared take 2ab plus b squared. First term squared, twice the product, plus second term squared. The product here is a negative here. Okay, so let's take out a common factor here. We take out a common factor, I've got b squared outside of cos squared plus sine squared. That's pairing these up. Okay, and then we've got the other two terms there. So cos squared plus sine squared is 1. So that's 1b squared, take 2ab cos c plus a squared. Oh, can you see what we've just done? Let's put these two sides up the front. So c squared, the square of a side is the sum of the squares of the other two sides minus twice the product of them cos of the angle opposite it. So if I had angle C, I could find the side opposite it here without knowing any other angles. I would have to know these two sides though. That's interesting. What marvels we can do even without 90. Without a 90 there. Come on down and let's have a look. So in any triangle, we didn't have to use angle C. We could use angle C. It says the side opposite C, c squared, equals the sum of the squares of the other two sides minus twice the product cos of the angle opposite. We need to know angle op to get a side, and the two other sides around it must be given. So it could be b squared, in which case we'd have to know a squared and c squared, twice them, and the cos of b. You've got to know the angle opposite. So if you want to get a, that side, a squared would be b squared plus c squared minus 2bc cos of angle a, the angle opposite. Hey, this is a bit complicated, but it's going to be a powerful tool. You only need one angle and you can find a side, or you maybe with three sides you can find something. Let's have a look. Here we are in words now, and this is a generic approach. This is very important. A generic approach in maths formulae. Don't just base your knowledge in a triangle ABC. When you do, see that c squared means the side opposite the chosen angle. Must be opposite in the cosine rule. Is the sum of the squares of the other two sides minus twice their product cos of the angle chosen. So you must know the angle opposite. Okay. So think of these words so that you're not just based in ABC land. Could you do PQR? Do you want to pause the presentation and tell me about finding P? This would be little r and this would be little q. Let's have a go. Little p squared equals sum of the squares of the other two sides minus twice their product cos of the angle opposite. So that's the equivalent rule in PQR land. Let's have a look at some examples now. Okay, here we have it. find all the unknown angles and sides. Well, what we're going to do first of all, let's find t using our new rule. T squared is sum of the squares of the other two sides minus twice their product, cos of 80. Work it all out, there we have it. But we've got to keep all these decimal places in there. Maybe just leave it on the calculator with all the decimal places, not even truncate it to 4. Now use the law of sines, okay, because we need an angle, and that would be the best way to find an angle. So this is the biggest side, opposite the 80, so we can find either of the other two. Let's do the one up the top here. So the sine of that, oops, sorry, no, what one are they doing here? Taking it from Pearson's, doing this one in here. The sine of that over its opposite side is the sine of 80 over its opposite side. So therefore multiplying across, there's its sine, inverse sine, and we have the angle. So we've been a combo now. And so by sum of angles of a triangle, we can find the other angle. All right, so what have we done? We've got a side and the two other angles. We've solved it. And here's Pearson's hint, what I've just been talking about there. As previously mentioned, remember to store immediate answers and then just shift on the Casio. You can shift the key and recall the answer for the next line of calculation. Don't round off until the final answer, because you will carry an error through each rounding that you do. Okay, so let's have a look now at the next one, example 21. A ship travels 50 kilometres due west. Okay, have a little north-south thing here, 50 kilometres due west. Okay, here's the departure point, west is that way, and 50 kilometres, then changes its course to 18 degrees northward, swings 18 degrees northward, and goes 75 kilometres. How far is the ship from its point of departure? So we want D there. Have we got enough information? Okay, so let's have a look and have a look at what angle we've got. We've got this one, haven't we? Because sum of angles on a straight line says this will be 180, take 18, or 162. And so using the cosine rule, d squared, sum of the squares of the other two sides, here we have them, minus twice the product, cos of the angle. And we have that total distance then. Powerful stuff. Okay, we can either take it to, oh yes, it says to the 1/10 of a kilometre, so we've taken it there. Okay, let's look at another idea here. Obviously, if we're given three sides, we can put them in here and we'll just have cos C left. In the information booklet, they do actually provide this rearrangement. Let's rearrange it. Let's put this term over on the other side, and therefore and then bring the c squared across. So a squared plus b squared takes c squared, putting the c squared over there and making that positive if you like. Cos of angle C now, dividing by 2ab. So we're rearranging this original expression. So you can find the cosine of C if you knew all the other sides, all the sides, and then do it on the calculator, inverse cosine. So this is a good one to use on your biggest angle, because as we said before, if you work with the cosine, you know when an angle is equivalent to this, might have the same size value, but it's gone big. Why? Because in the second quadrant, its x value, which is the cosine, will be going negative. So it will tell you whether the angle is bigger than 90. So try to find the biggest angle of a triangle using the cosine rule, if you're lucky enough to have enough information. Let's have a look at an example here, and then some for you to do. Here's PQR, and let's try and work out a starting angle. So what's a starting angle? Let's try angle P. Okay, so the cos of angle P is 5 squared plus 6 squared, sum of the sides around it, minus the side opposite, over twice the product of the sides around it. So it's not a bad idea to think of that rule in terms of sides around it, and side opposite is the one that's taken away. Think of it generically. So we've got the angle now. What can we do? Let's go and find another angle. So we won't find the biggest one. That's that one there. We'll go here. So the sine of Q over the side opposite is sine of the angle we just found over 4, and multiplying across we can find the angle. So the sine and cosine rule are a powerful combination. Inverse sine there to find that. And then, of course, always the last angle. Don't work it out. With sine and cosine rule, use sum of angles of a triangle equal 180 degrees. Take the other two away. And then you do your rounding only at the last level there. Okay, we've got two powerful tools here now, haven't we? Really powerful. Let's come down and do a final example now. A ladder is 8 metres long, leaning against a non-vertical wall. The wall doesn't look too healthy, mate. The ladder is 3.5 metres from the base, and the distance of the ladder down the wall is 5.75. So they've really made it difficult for us because we don't have a 90-degree triangle here. Find to the nearest tenth of a degree the acute angle of the wall to the horizontal. That's that one in there. How much is the wall slanting? Okay, well, let's look at our triangle. Let's maybe draw it again like this. We've got 3.5 metres, 8 metres, and 5.75 metres. So we want the angle in here. So let's go for this one. And it's the biggest angle of the triangle. Are we worried? No. Because if it is bigger than 90 degrees, as certainly is indicated in the problem, then the cosine should go negative. Let's just check it. The cosine of this angle in here is the sum of the squares of the sides around it minus the square of the side opposite over twice the product of the sides around it. Don't put A, B's and C's in necessarily. Know sort of generically the formula. So if we do the inverse cosine of that on the calculator, don't take it out as a decimal and then put it back in again. Just put cos neg 1 or cos neg 1 of your answer, and you get 117.664. And of course the angle you want is sum of angles on a straight line, 180 minus that, plenty of decimal places, and then round it at the end. So you can do some good stuff with this non-right angle triangle work, and it's far more practical because, you know, lots of, let's say, bearing problems don't have 90-degree triangles. Angles between two towns and so on are unlikely to come out just to be 90. All right, so let's go down and have a go. Before we do, there's a screen clipping from the IB information booklet. The cosine rule is put first. There it is in its rearranged form. Think about it generically. A side squared is the sum of the squares of the other two sides minus twice the product of those sides cos of the angle opposite. That's how you think of it. Cos of the angle opposite, a side, is the sum of the squares of the sides around it, not opposite it. Take the side opposite squared over twice the product of those sides. Notice in the sine rule, they do not turn it up the other way. Because if you're looking for an angle, then you might have that angle on top. So if you're looking for angle C, put it on top. You'll know all these, let's say, and multiply across by what's on the bottom. It's easier to solve an equation if the unknown is in the numerator. So the IB don't offer those two alternatives, but you should think of them. And the area of a triangle here is what? Half the product of two sides, and the angle must be the angle included. So please think about these formulae generically in word terms, not particularly based on triangle ABC, because you may get a triangle PQR. So interpret them in a generic way. Okay, here's some problems for you from Pearson's, and again the solutions are underneath, so just go back there. That's the first 13. So you can play with these. These aren't all that important here, stating the number of triangles, but certainly 7 to 15 is, are important problems to solve the equation, solve the triangles completely. That's all angles and all sides. Okay, so pause the presentation, have a go. Going to go down now. Go down to 19. And then we'll go on now. 20 to 24 there. And then 25. And now we'll go to the solutions. All right, so there's a bundle up to 7. We haven't got down the left-hand side there yet. Four, 5, the rest of 7 there. Eight. Try and get 9 and all of 11 in there. And some other comments here on 11. Number 12. It's a bit messy doing it this way. Thirteen. Okay, now they're just in single format now. 14. Rest of 14. So if we can get all of 15 in, no we can't. Rest of 15. Sixteen. Let's go to 17. A bit more of 18 in a minute. Few different methods there. $19. $20, 21 and 22 all there. 23, most of 23. Most of 23 there. $24. And as we go to 25 there. So you've got a lot of powerful techniques there, so think about them, work on them, be aware of what's provided for you in examinations in the information booklet from the IB. So I hope you enjoy doing those problems. I'll catch you in one further presentation for topic 3 as we wind it up, and some practice questions at the end. But for now, it's cheers from me.